Welcome to the Math 154 videos. This is going to be talking about the squeeze theorem, which I have written up here. So we have if f of x is less than or equal to g of x is less than or equal to h of x when x is near a, and the limit as x approaches a of f of x is equal to the limit of h of x, which we'll call L, then we can say the limit as x approaches a of g of x is equal to L. Now let me just draw a little picture for you guys so you can see sort of exactly what that means. So we have a function f of x on the bottom here, and we have a function h of x on the top here. So we'll label those, and this is f of x. And then we'll have this function g of x that's right in the middle. So what this theorem is saying is at this point here, a, we have the limit as x approaches a of h of x and f of x are the same. So it sort of sandwiches or squeezes that limit of g of x to be the same thing. So that's pictorially sort of what that looks like. Again, depending on your functions, it could be slightly different, but that's basically the concept. So let's take a look at this example. Now if you'll notice, we have this f of x in the middle. So that's actually our g of x. Sometimes they use different functions, labels for the functions. So whatever letter it is, that doesn't really matter. What matters is we have one on the left, one on the right, and one in the middle, right? So there's one on top in the graph, one on the bottom of the graph, and they're sort of bounding the one in the middle. So we can just go ahead and call this our h of x, and let's just call this capital F of x instead of lowercase f, because we have that in the middle this time. So we want to check now that this limit and that limit are the same. So here in our example we have a big f of x, but that's really not too much of a problem. We'll go ahead and calculate those limits. So here we want the limit as x approaches 1 of our middle function, so we better check the limit as x approaches 1 of our function that's on the bottom. So that would be 6x plus 2, and if you notice, that's just a polynomial, so really we can just plug in 1. 6 times 1 is 6 plus 2 is 8. Then we'll check the limit as x approaches 1 of our h of x, which is x squared minus x plus 8. So 1 squared minus 1 is 0, so we actually get 8 for that one as well. So since these two functions, capital F of x and h of x, approach the same limit, then they sort of squeeze the middle function, f of x, to force it to go to the same limit. So we have, by the squeeze theorem, that the limit as x approaches 1, in this case was our a value, of f of x, which we don't really know what f of x is, but that doesn't matter. We know that its limit as x approaches 1 is going to be equal to 8. And now notice we covered all the bases here. So we have, if we have 3 functions, 2 sort of bounding the other one when x is near a, well, we had that. We were given that, and then we have the second condition, the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x. That's what we had to check over here because it wasn't given to us. Since we've satisfied both of those conditions now, then we can draw this conclusion at the end. So here's our second example, and if you'll notice, they're asking us to prove that this limit is equal to 0. Now, if we try to plug in 0, we'll see that this 5 over 0 here is undefined, so we can't actually do that to evaluate the limit. So this is where the squeeze theorem sort of really comes in handy. Now, our first condition of the squeeze theorem is if f of x is less than or equal to g of x is less than or equal to h of x. So basically, we're looking for this whole function here to be our g of x. We want that to be in the middle and see if we can find two functions that bound it from below and above and then satisfy these limit conditions, we can prove this limit. So, our first thing to notice is that cosine of x is between negative 1 and 1 for any real numbers, x. Okay, so 5 over x is still going to be a real number. We're actually not, it's not going to change this inequality any. So we're going to use that and say that negative 1 is less than or equal to cosine of 5 over x, right, because that's a real number, which is less than or equal to 1. So now, we have three functions, and we almost have g in the middle, but what are we missing? Well, we're missing this x squared right here. So why don't we just multiply the entire thing by x squared? So we'll get negative x squared is less than or equal to x squared cosine of 5 over x, which is less than or equal to x squared. Okay, so now we can call negative x squared our f of x, and we can call x squared our h of x, and we have two functions that are bounding our middle function g of x. Well, that's our first condition that we need for the squeeze theorem. That's really good. So now we got to check and see if they satisfy the next one. So let's take the limit as x approaches a of f of x, which is negative x squared, and our a value in this case here is 0. So really, we're looking for the limit as x approaches 0 of negative x squared. Now x squared is just polynomial, so we can just plug 0 right in, and we get 0. Now we'll do the same thing as x approaches 0 of our h of x, which is x squared. And similarly, that's polynomial, so that's just going to be 0. We plug 0 in. So great, we found the limit of f of x is equal to the limit of h of x, both as x approaches 0. And that means our L value here, so really this is our L in the theorem. And so that means the limit as x approaches 0 of g of x is also equal to L. So that's by the squeeze theorem. We'll label that as ST. By the squeeze theorem, the limit as x approaches 0 of x squared cosine of 5 over x equals 0. And therefore we have proved what we wanted. So make sure when you do your answer, you always write that it's by the squeeze theorem. Okay, so we had to look for both of the premises. We have two really big conditions that we have to satisfy first. So if we satisfy both of the conditions, then the conclusion follows by the squeeze theorem. So just make sure you notate that right in your answer, and therefore we have proved that limit.